So, hello everyone again. This is lecture number 5 part 1 of semiconductor electronics materials devices and simple circuits. So, in this lecture we will start with our further discussions on semiconductor diodes. So, let us finally begin the discussion here directly. So, I am Sameer Lavankar, let us begin our discussion. Okay, so right now we are on the sixth topic, that is semiconductor diode. Okay, so previous to that we have understood introduction, in which we understood what were the basic initial semiconductor devices which are called as your cathode ray tubes. We understood what were the specifications of cathode ray tubes, what was the size of cathode ray tubes, and we compared it with the modern chips, IC chips, integrated circuits basically. Then the second concept about classification of metals, conductors and semiconductors, we basically classified how to define, as in what material can be said as conductor, semiconductor, insulator, etc. Then we also understood a concept of conduction band, valence band, energy gap, band theory of solids, etc. in this concept. Then we understood two types of semiconductors. One was your intrinsic semiconductor and another was an extrinsic semiconductor. In extrinsic semiconductor we understood two different types of this also. So, one was called as your N type and second was called as your P type. Okay, so one were called as your N type and second was called as your P type. Okay, so this being said, then we understood basically what is the meaning of N type. So, N type has a pentavalent impurity and P type has a trivalent impurity. Okay. So, that all things we understood in this extrinsic semiconductors, and then finally, we understood the concept of PN junction. Okay. In PN junction what we understood some processes also. Let me just iterate again. So, we understood different processes. First process was your diffusion, the second process was your drift. Okay. So, basically diffusion was happening when the initial electrons were being passed from an N type to a P type, or let us say the holes were passing from a P type to a N type, basically due to a concentration gradient, and because of this a depletion region was created in the between. So, this was your depletion region. So, this was basically your depletion region. Let us say this is the complete PN junction and this was a depletion region being created, and in this depletion region an electric field was being set up and inside that drift current was being applied. Okay. So, initially what happens is that the amount of the diffusion current is small, and then there is a time when the equilibrium is reached, when the diffusion current is equal to drift current, and then the amount of there is no net electric current passing through the circuit. Okay. Using all these concepts, we went to the initial right now concept which we are studying, that is the semiconductor diode. What is basically semiconductor diode? So, basically a PN junction which is kept inside two metallic contacts is basically called as your semiconductor diode. Okay. So, let us further keep discussing semiconductor diode, so that we can move to some other applications of this. Okay. So, semiconductor diode, as I already explained to you that when a PN junction diode along with this metallic contacts is basically called as your semiconductor diode. Okay. So, also we understood one of the concept in the previous discussion about forward biasing. What is bias basically? Bias is basically when an external applied voltage is called as your bias. So, let me just write it also. So, external applied voltage is basically called as bias. Okay. So, now the first concept which we understood in the previous discussion was about forward biasing. Okay. So, what happens in forward biasing, or what is basically called as forward biasing, when the positive terminal of the battery is connected to a P type circuit, a P type semiconductor, and the negative terminal of the battery is connected to the N type semiconductor. Then what happens is, when the current is being flowed through this circuit, then there is a decrease in the barrier potential, correct. So, if there is a decrease in the barrier potential, what will happen, that with the increase in the supply of the voltage, there would come a time where, with the increase in current, there will be an increase in the with an increase in the voltage, there will be an increase in the current. Okay. So, I think these all things are understood. So, initially the current would be small, and as we increase, so as we keep on increasing the applied voltage significantly, the barrier height will be reduced. So, what was basically barrier height? So, this initially the barrier height was your V naught, and then it decreased to V naught minus V, correct. It decreased to V naught minus V depending upon the applied voltage here. So, as we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have the required energy, and thus what is the basic fundamental conclusion of this forward bias, that with the increase in the voltage the current increases. Okay. Fine. Let us look towards more of the results. Let us discuss more about this forward biasing, and then we can move on to reverse biasing. Okay. Fine. So, this line, okay. So, due to the applied voltage, electrons from the N side cross the depletion region and reach P side, correct. So, what happens when the voltage is being applied, then the electrons which are being present here, they cross this depletion region. It is quite evident, it cross this depletion region, and where does it go? It goes or reaches the P side. Okay. Why? Because why it can be reached? Because there was some depletion region was having some barrier potential, that barrier potential is being reduced, and due to this reduction what happens is there is a movement of these electrons or the negative charges which are being present on the N side. Okay. Where they are minority carriers, quite evident, on the P side it is minority carriers. Similarly, the holes on the P side cross the junction and reach the N side, quite evident. What will happen this time? So, let me denote holes as only circles. So, what will happen? These are the circles here evidently, and they will reach in this direction. So, as there is a movement of the negative or the electrons from the N side to the P side, there is a movement of the this holes also from the P side to the N side. Okay. So, where there are minority carriers, quite evident. So, in the N side holes are the minority carriers. Okay. So, just for a revision I am writing again. So, for a N type, your electrons are majority, charge carriers. Similarly, holes are minority charge carriers. Fine. Similarly, for a P type, what happens is that electrons are minority charge carriers and holes are majority charge carriers. Okay. So, you can remember this using the name also. So, as the name is N here, N can be said as negative. So, hence the majority is for electrons, here the name is P, and hence the majority is for holes. Okay. Fine. So, let us move on. So, now at the junction, so this process under forward bias is known as minority carrier injection, quite evident. So, what is happening, that the minority carrier, so basically let us say for the first thing only, for the first point, electrons crosses N to P. Okay. So, what happens is there is a addition of the minority carriers, correct. So, there is a minority carrier addition to that side. So, let us say for an example, what is the minority carrier, minority charge carrier in a P type? It is electrons are being added upon P type. Similarly, what is the minority charge carrier for a P type? For minority charge carrier for a P type is electron, and for N type it is holes, correct. So, here holes are being added, and here or on the P type electrons are being added. So, what we can say, that the minority charge carriers are being injected upon. Okay. So, that is the only line which is written here. I think it is clear. I will again explain. So, what is basically happening, what is the minority charge carrier for a P type? For a P type it is electron, correct, and as you can see here clearly from the first two lines, that the electrons are being added up here. Similarly, for an N type semiconductor, what is the minority charge carrier? These are holes. So, you can see from the second line that what are being added here, the holes are being added here. Okay. Fine. So, this process under forward bias is known as minority carrier injection. Okay, injection. Now, at the junction boundary on each side, the minority carrier concentration increases significantly compared to the locations far from the junction. So, what they are saying is that at the junction boundary, so at this boundary what happens is, that the minority carrier concentration increases. So, at this location, what is for P? P is P electron. So, basically electron location or electron concentration is higher in this location, and positive charge concentration is higher at this location. Okay. Due to this concentration gradient, the injected electrons on P side diffuse. The injected electrons, so these are those electrons, these are the injected electrons diffuse from the junction edge of P side to the other edge of the P side. Okay. So, what they are saying that due to this concentration gradient, what happens is that the injected electrons on the P side diffuse from the junction edge of P side to the other end of the P side. Okay. So, there is a diffusion happening. So, there is a diffusion happening inside P only. Similarly, there is a diffusion happening inside N only. Likewise, the injected holes on the N side. So, these are the injected holes being talked about. So, injected holes on the N side diffuse from the junction edge of N side to the other end of N side. Okay. So, as you can see, these are the injected electrons and these are the injected holes. So, basically they try to move apart from its location, okay, to the other side. Fine. So, this motion of charged carriers on either side gives rise to current. Quite evident. What is basically current? Current is due to change in the charge concentration per unit time. So, if there is a change in the charge, if there is a movement of the charge per unit time, then there will be current involved. If there are some electrons here and there is a movement occurring, if there are some holes here, there is a movement occurring. So, basically there is a movement of charges happening and hence there will be current produced. So, this motion of charged carriers on either side gives rise to current. Okay. The total diode forward current is the sum of hole diffusion current and conventional current due to electron diffusion. Okay. So, what will be total diode current? Total diode forward current they are talking about. Okay. It will be sum of hole diffusion current. So, hole will be diffused and conventional current due to electron diffusion. Okay. So, due to diffusion of current also, diffusion of electron also and a diffusion of this holes also. Okay. The magnitude of this current is usually measured in milliamperes. Okay. So, why it is told as milliamperes, we will understand when we will understand reverse bias also. Okay. So, what is the magnitude of current involved here? The magnitude of current involved here is in milliamperes. Okay. Fine. So, that thing being said, let us move on with a further discussion. Let us now understand the reverse biasing. Okay. So, basically what was forward biasing? So, in forward biasing what was happening is that the positive, this was positive, this was also positive, this was negative, this was also negative. So, now if we just change the polarity of the applied voltage, so that is nothing but called as your reverse bias. So, that is nothing but your reverse bias. Okay. So, as you can see here. Fine. So, let us try to understand this now. So, basically when an external voltage V is applied. So, this is the external voltage V which is applied. So, when an external voltage V is applied across the diode such that the N side is positive, and the P side is negative, it is said to be reverse bias. So, that is the definition of the reverse biasing. Now, let us understand what is reverse biasing. So, the applied voltage mostly drops across the depletion region. Okay. So, as you can see that the majority of this is dropping where? Inside a depletion region. So, here also you can say that for forward biasing also the applied voltage mostly drops across the depletion region only. Okay. So, the majority of the resistance which is being offered is by the depletion region only. Fine. So, it is the same for both the cases. Now, the direction of the applied voltage is the same as the direction of barrier potential. Okay. So, what is happening basically, we can understand that there was a force which was acting upon here. Now, if we are applying the voltage in the same direction, then what would happen? This barrier potential will increase, correct. So, the direction of the applied voltage is the same as the direction of barrier potential. As a result, the barrier height increases. What was happening in the forward bias, the barrier height was decreasing. This time what is happening, because the voltage, because the external voltage is also acting in the same direction, that is why there is an increase in the barrier height. Previously what was happening was that let us say this was a barrier potential and the external applied voltage was in this direction. So, that is why because of the differences in this voltages value, the barrier height was decreasing. This time it will increase. Okay. So, the direction of the applied voltage is same as the direction of the barrier potential. As a result, the barrier height increases and the depletion region widens. So, as you can see from this diagram, and you can see from this diagram for forward bias, the depletion region is small for a forward biased and depletion region is very high for a reverse bias. Okay. So, the depletion region widens due to the change in the electric field. Okay. So, the effective barrier height under reverse bias is V naught plus V. Okay. So, these are the different points of concern you should remember when we are understanding the difference between a forward bias and a reverse bias. Okay. So, first thing to be understood is, first of all, what is the first point of difference? The first point of difference is that in a forward bias, the N type is connected to a negative terminal, the P type is connected to a positive terminal. Okay. What happens in a reverse bias? The N type is connected to a positive terminal and the P type is connected to a negative terminal. Okay. The second thing is that the external applied voltage in a forward bias is opposite to the barrier potential, but in the reverse bias, the applied potential and the applied voltage and the barrier potential is in the same direction. Okay. The third thing is that the barrier height reduces in forward bias, that is equal to V naught minus V, and the barrier height increases in your reverse bias, which is V naught plus V. Okay. So, that being said, let us now understand further discussion about this. So, due to this, because there is a decrease, it is quite evident that the current will decrease, correct. So, this suppresses the flow of electrons from N to P and P to N. So, quite evident that now the force required for these electrons, or the energy required for electrons to go from this place to this place, or let us say the holes to go from this place to this place, will increase, correct. So, this suppresses the flow of electrons from N to P and holes from P to N, quite evident. Thus, diffusion current decreases enormously compared to the diode under forward bias. Okay. So, what is it is said, diffusion current decreases. What decreases? Diffusion current decreases enormously compared to the diode under forward bias. Okay. So, diffusion current was basically to the concentration gradient which is happening, but because of the increase in the because of the increase in the depletion region, there is a decrease in the diffusion current. Okay. So, the diffusion current decreases enormously compared to the diode under forward bias. The electric field direction of the junction is such that if electrons on the P side or holes on the N side. So, electrons basically that which are your minority charge carriers on the P side or holes on N side again minority charge carriers, in their random motion come close to the junction. Let us say they come close to the junction. Okay, they will be swept to its majority zone. Okay. So, because of the force which is being acted upon, or the electric field which is acted upon, they will sweep into its majority zone. So, this will go here and this will go here. So, what does it mean? That the drift current is very high here. Okay. So, this drift of carriers gives rise to current, but because these are minority charge carriers, the amount of current which will be produced will be very less as compared to the diffusion current. Okay. So, this drift of carriers gives rise to current, and as you can see clearly that this drift current is of the order of only few microamperes. If you remember correctly, for forward bias it was in milliamperes, but for your reverse bias it is just in few microamperes. Okay. This is quite low. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. So, because the charge carrier concentration is only and only happening due to the minority charge carriers, that is why this is only in few microamperes. Okay. So, that being said, let me close this discussion here only. We will continue with reverse biasing in the next part of this lecture. Okay. So, thank you so much for this.